Welcome to Finding Areas in Polar Coordinates. We will start by looking at double integrals, and then we will convert that to an iterated integral in polar coordinates, and then we will see that we can write it as a single integral. So let's see how we can find an area using a double integral. Suppose we have a region R in the xy plane, let's say, and it's two-dimensional. Then we can find the area of this region R by just integrating 1 over that region R, the integral over R of 1 dA. So we can say that the area of a region R is just the double integral over R of the function 1. So let's see how we can use this to find the area of a region in polar coordinates just in terms of a single integral. I mean by that a one variable integral. So let's suppose that the region that we're going to find the area of is this pink region here. And it's defined to be the region between the two lines or rays theta equals alpha, theta equals beta. It's bounded up here by a function r equals h of theta. These two rays go through the origin, and so this is the region right here. Well, in that case, we can say that the area of this region R is the integral over R of 1 dA, and then we can write that in terms of a double integral in polar coordinates. How do I integrate 1 over this region? Well, it'll be the integral where theta goes from alpha to beta. Theta equals alpha, theta equals beta are those two rays. R goes from 0 to h of theta. R equals 0 is down here. R equals h of theta is up here. And we integrate 1. And with respect to the area sub-element, that's going to be r dr d theta. So we look at this and we're integrating r dr, and so let's just use the fundamental theorem of calculus. This inside integral then is an antiderivative of r, which is 1/2 r squared, and into that we evaluate it at h of theta and r equals 0 to h of theta and subtract. So let's see what happens if we do that. What we get then is 1/2 h of theta squared minus 1/2 0 squared, which is just 1/2 h of theta squared. So what we then get is this single integral, which is equal to this single integral. The integral theta goes from alpha to beta, 1/2 h of theta squared d theta, where h of theta is this boundary up here of this region R in here. So suppose we have a region like this. Here is a curve r equals cosine of theta. Here are two rays, theta equals pi over 4 and pi over 6, and the region R is Carolina blue right in here. So let's see what we can do with that. We have, by what we saw so far, the area of R is going to be 1/2 the integral, if we pull this half outside that is, the integral of theta equals alpha to beta, h of theta squared d theta. So h of theta is the cosine of theta. So this turns into 1/2 the integral from pi over 6 to pi over 4 cosine square theta d theta. We have, hopefully all of us have seen how to integrate cosine squared of theta, and we can also do that integral in using sage math. And so let's see what we can do with that. In sage math we can write the command 1/2 times the integral of cosine of theta quantity squared, where theta goes from pi over 6 to pi over 4. And when we hit Shift Enter to execute this cell, we get the output being 1/48 pi minus 1/16 times square root of 3 plus 1/8. So that, which is equal to this integral up here, is our area. So the area is pi over 48 minus square root of 3 over 16 plus 1/8. If we look at these three fractions denominators, we can see that the lowest common denominator in this case is 48. So pi over 48 is pi over 48. 3 square root of 3 over 16, if we multiply both numerator and denominator by 3, that's going to give us minus 3 square root of 3 over 48 here, plus 1/8. If we multiply both numerator and denominator by 6, that's the same as 6/48. So combining all of those fractions together, we get pi minus 3 square root of 3 plus 6 divided by 48. This is kind of an interesting answer if you look at it. R equals cosine of theta does turn out to be a circle. And so what we found was the area of this little region inside that circle. And it turned out that the area involved the number pi. It also involved the number square root of 3. And it also involved just an integer divided by 48. So this is, I think, kind of an amazing answer because it has both an integer, a square root, an irrational number, which is square root of 3, and it also involves pi. So notice that this was pretty easy. We were just able to set this region's area up as an integral just involving a function of theta times d theta, where this outside curve was h of theta. I'd like to say thank you for watching this video. I hope you enjoyed it and found it instructive. For more info on the relation between double integrals and iterated integrals, I have another much longer video on the fundamentals of that on YouTube. And please stay tuned for more of my videos, which should involve some math and physics. Have a good day.